Okay, good morning, ladies and gentlemen. Welcome to APAC DNS Forum 2024 pre-event webinar. This webinar is around DNS delegation security led by China Internet Network Information Center, Jinan University, Computer Network Information Center, Chinese Academy of Sciences. And thank you, Dr. Zhiwei Yan, for initiating this webinar, and thanks for all the colleagues' hard work for this session. I am Dongjie Liu from Jinan University, Guangzhou, and I'm the moderator for today's session. Today, we are very glad to invite 4 experts to give us speeches on different topics. Now, let me introduce our first speaker, Mr. Lingjian Song, who is a senior DNS architect and manager of the IPv6 project in Alibaba Cloud. Beyond his professional responsibilities, he actively contributes to the broader community through his involvement as the former CTO of the IPv6 Forum's China office. As member of the ICANN RSec caucus and as coordinator of the Yeti DNS project, today we are very honored to have Mr. Song to give us a speech entitled "Who Forged My DNS Answers?" He will introduce the event of DNS hijacking and how we trace the issue. Now let's welcome Mr. Song.
Hello, can you see my screen?
Yeah.
Okay. Thank you for the morning. Thank you for the host. And hello everybody. My name is David Song, and I'm from the network infrastructure team at Alibaba Cloud. Currently, I'm heading a team that specialized in addressing DNS anomalies resulting from the third-party interventions, including network outage, no response issues, and incidents involving faulty response. Today, I'm truly honored to be invited here and to share our practice to troubleshoot DNS hijack issues from our real case. Before we dive into the DNS and the hijack problem, let's have a look at these pictures. It's a skyscraper in Beijing with a splendid design if you happen to be here in Beijing, and a solid, stable base is meant boast for the building, However, the people working and living in this building normally do not pay much attention to the base unless something gets wrong. The same with DNS. Though DNS is a fundamental component of the modern internet infrastructure, it remains one of the most overlooked elements. And people say that the DNS is still the Achilles heels of the internet. Let's investigate how DNS works. Suppose some audience are not technical guys. In a nutshell, the domain name system, DNS, is the phone book of the internet. It translates human-readable domain names, for example, who.com, to machine-readable IP address, of course, and other internet resources. As the diagram shows, when a user client would like to visit who.com website, he starts asking for who.com to a DNS reserver, which is configured by himself, automatically assigned by his network operator. Like a proxy, the DNS reserver helps the user to search the DNS answer recursively from the root server, .com server, and down to the food.com server, following the delegation chain. Because the topic of today's session is DS delegation security. So today we will explore what happened during the delegation and what's wrong with it. Return to the resolution loop. When the reserver gets the answer IP address, it will return to the user. The user then will make a connection to the website they want to visit. It's very simple, right? But it becomes difficult when something gets wrong because the troubleshooting DNS is very difficult. DNS was invented 14 years ago, more than 14 years ago. And I have seen many people still struggle with debugging DNS problems. There are many issues you may have with DNS. For example, issue related to no response and the issue related to DNS hijack and forged answers. Today, we will focus on DNS hijacking and spoofing issues. Before the user get the right answer, there are a lot of DNS interactions and communication happen. The communication can be intercepted because most of DNS queries and response are not encrypted. The DNS answer in the case of DNS reserver can be poisoned as well because not all DNS are DNS enabled or signed, or the reserver not open the validation for the domain. So if the user get the forged answer, it will be redirected to malicious website, which may contain malware or steal user data like password. It's very difficult to debug the problem and find out who forged my DNS answers in this case. So today I would like to introduce the real case I faced by the end of last year. Their customer claimed that their DNS reserve with unexpected results, and their website was hijacked to a website that located outside of China and with some gambling information, and some occasionally will be redirected to some a website with adult information, So my team successfully assisted the customer in resolving these critical issues. That issues resulting the customer in monthly loss amount to millions. There are 3 steps we have done to solve the problem. Firstly, we reproduce this issue using our props, hundreds of them, to make sure the DNS answer was forged in certain network, and continually to observe the issues. And we also, by editing the host file, change the victim's name to the malicious IP address, we can open the redirected page of malicious website. Secondly, we discovered that especially the traffic to root and .com servers, the query with the QNAME of victim of customer received the random forged answers. So that's because the delegation features that all traffics go to the root if the cache miss happen. To address this, we created a DNS trace route, a tool designed to trace the path of DNS query to pinpoint the source of the hijack, similar as how trace route works, the command trace route works. We will dive into that part later. Finally, we've outreached the responsible company and located the server cluster and resolved the problem with our concerted effort. So let's go through the process how we debug the problem. Firstly, we use dig command. I think DNS guys use dig command frequently, oftenly. And dig command with trace option can mimic what DNS resolver does when it looks up a domain. It starts at the root servers and then queries the next level of name servers like .com and secondary level DNS servers. And until it reaches the authoritative name server for the domain. As the diagram shows that when the client dig for the .com with the trace option, it only receives the DNS referral until the full .com authoritative name server provides the DNS answer. Mention that it's worth to mention that the DNS referral means that the server on the top level or the root level, root server do not have the exact answer you need to return to the user. So the referral means you need to ask the next one. Okay, when we dig the victim name with trace option enabled, we found that both the root and the .com authoritative occasionally provides a DNS response that include a record. That's the problem we observe. The DNS response from root and .com authority server is intercepted. It proved that. The forged answer is to be cached by any reserver who asks the name. That's why response from many public DNS was forged from our observation. We try and change different names to test the interception behavior other than our victim's name. We found that the anomaly disappeared. So that proved that the DNS interception in this case only aimed at certain victim's name. However, we still have the problem to debug what happened in between. There are multiple paths between the testing clients and root server and .com server, and there are multiple hopes in each path. It would be nice if the device in the middle can tell us where the problem is. So we sort of how traceroute command works. As a background, I will introduce that a little bit. The traceroute command ping each network device in between to say which help is run. It simply makes the magic by manipulate the TTL, the time to leave field in the IP packet header. Whenever an IP packet is forwarded by router, the TTL is it's increased, and when the TTL is as the IP packet is forwarded by each hop, it will decrease by 1. When the TTL is 0, the IP packet will be discarded, and the TTL exceeded by ICMP will be sent back and tell the IP address of that router. That's simply how it works. Note that the traceroute can also use UDP at port 15.3 to test whether the packet will be dropped or not. But it cannot help the interception case we have, because we're pretty confident that the interception device on the path will read the queue name of that DNS queries. So intuitively, we create a DNS traceroute tool with the concerted effort with Alibaba team and the Tsinghua Network Information Security NAP. The difference between the DNS traceroute and the conventional traceroute command is that the DNS traceroute uses the IP DUDP DNS packet with incremental TTL instead of IP ICMP packet. Like the diagram shows, the testing client will continue send DNS query with increasing TTL from 0 to 30 until it receives the DNS answers. When it receives from the real server it's query against, it will stop. That's the normal case scenario. Suppose that there is a bad guy on the path who forged the DNS answer aimed at a certain query name. That's the case we faced. It's simple. It's a simple model of the hijack case our customer has. We send DNS query with increased TTL. It received forged answer when TTL is in this case, in this diagram, we suppose that the second hope of the routing path is where forged answer. And as well, it will receive the TTL exceeded every hope as it works, as it designed. We will continue to receive the forged answer and the TTL exceeded ICMP message when TTL is increasing. It tells that the hijack is on path interception, which means the DNS traffic is monitored silently, and the normal DNS query are not dropped or modified and forward it to that server you asked. The forged DNS response is generated when it's necessary, and the forged DNS response will be received by the client before the real one. And yeah, that exactly like the diagram shows. Yeah, it receive forged answers, and finally it will receive a real DNS answer, valid answers finally when it reach the real name service. So in this diagram, the client received 3 forged DNS answers and 1 true DNS answers. There's another real on-path interception example. You can test it when you try this method. We trace the victim names against one root server. The command report first forged DNS response was received when the TTL is 10, and the IP address is pinpointed as well. Okay, let's wrap up the troubleshooting result we have found. We use a dig plus the trace finds specific DNS query to root and the com servers, receive a random forged answer which will be cached by reservers. And the DNS trace root tools print the path of the query forwarded and pinpoint the IP address or the prefix, the network's subnet, which will forge the answers. The the trace root tool also indicate that the presence of the on-path interception. The hijacked devices respond with a forged answer in advance, silently, ahead of the legitimate response. Before I finish my talk, I have some words, the last words. Today we've observed individuals, companies, even authorities adopting measures like firewall to combat DNS abuse and online fraud. It's okay, but that measures contribute to the internet becoming more complex and increasingly unpredictable. Some malicious guys, attackers, will take advantage of this. And some of them will leave holes in the internet, leaves holes in the firewall of the internet. We observe the DNS anomalies happen every day around us. Together, we must diligently safeguard our DNS environment through our collective efforts and collaborations. Okay, that's all for my presentation. Thank you.
Thank you, Mr. Song, for your enlightening speech. And I guess we have a few minutes for questions. Anything you want to communicate or ask?
Okay, can you help me?
Yeah.
Hello.
Yeah.
Okay, so first, thank you for your interesting presentation. And I'm a first-year graduate student. I also do some research in the DNS security, which is really an important academic subject. And I know that you are a senior engineer in Alibaba Cloud, so I want to know that is the enterprise very concerned about the DNS security, and are there some research team to study DNS security in the enterprise?
Yeah, of course. As when I started my talk, I gave you a picture that the DNS is the fundamental, the base of the whole digital buildings, the ecosystems we have today. Usually people will not notice that the importance of the DNS. If you look into the real, how to say, the operation and the real cases of the anomalies and security events, you can see that DNS security is very important, and also sometimes the problem is not obvious, it's not noticeable. Some of the attacks were doing silently, and undermine the customers and the digital economics. We see that in large words. Yeah, and I noticed that some research look into that and found out what happened not only in the iceberg that we observed above the sea water, right? But also the huge ones under the sea. As you ask that, what's the attitude? What's the work we are doing in the enterprise like Alibaba? I can tell you that the stability and the security of our services is our how to say the red line of our services to commitment to the customer. If your services is not stable, is have the flaws in security, it's a very big thing. So Alibaba Cloud, Alibaba DNS team collaborate with the Tsinghua universities and Zhejiang universities and other research entities to try our best to move faster than the attackers to spot, to pinpoint the problem, to review the issues and the risk in the DNS that we are running, we are operating. So yeah, that's my answer to your questions.
Okay. Thank you for taking time to answer my question. Thank you.
Okay, thank you. Thank you, Mr. Song. Since our schedule is rather tight, let's just move on to the second speech. First,
okay.
Please, yeah, thank you. First, please allow me to introduce the speaker first. Dr. Baojun Liu is an assistant professor at the Institute for Network Science and Cyberspace of Tsinghua University. His research focuses on cyberspace security and has been recognized with awards and publications in top network security conferences. He leads multiple national research projects in China as a principal investigator and serves as a member of the ICANN RSEC caucus. Today, we are very honored to have Dr. Liu to give us a speech named Wolf in Sheep's Clothing, evaluating security risks of the undelegated record on DNS hosting services. Dr. Liu and his group review an emerging threat model of covert communication that abuses the reputations of popular domains and DNS hosting services. Through large-scale measurement, they confirm the abuse of undelegated records is widespread in the world. Let's welcome Dr. Liu.
Hello, everyone. I'm Baojun from Tsinghua University. I know that this topic of this session is about DNS delegation, but today I want to share our study about undelegated record. It is a research study that published at last year's IMC conferences. The title is Evaluating Security Risks of the Undelegated Record on DNS Hosting Services. In one word, in this research, we discovered a tech that have been overlooked by mainstream DNS hosting providers, and we proved it has been abused at a large scale. To start with, DNS hosting is an emerging third-party service like Alibaba. The vendors such as Cloudflare and Amazon provide infrastructures to support the resolution of hosted domain names. More importantly, they simplify the complex works for their customers to manage domain names. Yeah, so far so good. But however, victors tend to not verify ownerships of hosting domain names and make the DNS hosting service easy to use. Such a structure facilitated the issues of undelegated record. We name it UR. Let's start with the example. In general, a reserver conducts recursive queries to get the result of google.com, follows the delegation of DNS spaces. However, an attack can host google.com at Cloudflare due to the lack of ownership verification on Cloudflare platform. Actually, anyone is able to configure the undelegated record on the public, this hosting platform. As a result, a client, such as a compromised machine, can get the undelegated record at Cloudflare through a direct query. So, what can an attacker do while abusing this kind of undelegated record? We assume that a compromised machine is protected by a lot of defense mechanisms, for example, firewall or IDS. The attack aims to help the compromised machines bypass this kind of defense and get the information from the attack. For example, follow the C2 command from the attacker. An attacker can deploy a malicious mem server and configure the DNS record to provide this kind of information. But we believe that both the server and the domain names queried by the compromised machine have a low reputation. Therefore, this kind of the defense mechanisms can detect this kind of queries from the compromised machine easily. But how about hiding this kind of information in undelegated record of google.com at Cloudflare? Where this kind of compromised machine gets the undelegated records, the defense mechanisms observe the query from a renewed domain names toward a renewed DNS servers. As a result, the compromised machine can bypass this kind of defense mechanisms and get the information from the attack. Now let's move to the measurement of this kind of attack. The main challenge of this kind of measurement is to filter the undelegated records that do not belong to abuse. To overcome this kind of challenge, we provide a 3-step method. The first step is to respond. We name it response collection. We collect undelegated records from popular hosting providers with additional information for further determination. The second step is to determine suspicious undelegated records. Apart from excluding existing correct and protective undelegated records before, we also exclude the extended ones by using the concepts of uniformity. The last step is malicious behavior analysis. We checked if this kind of related IP addresses are malicious to label a malicious URL. Especially for A record, the IP addresses are used in the record. For TXT record, we extracted the IP addresses embedded in the text of the record. We first check if IP address is malicious by checking third-party threat intelligence and the IDS alert while checking sandbox traffic. Let's move to our measurement result. We conducted the 2 measurement studies for A record and the TXT record that belong to undelegated. And we collected the undelegated record from the top 2,000 domain names that belong to Tranquil popular domain name list. And we found that about 9,000 name servers hosting over 15 domain names in the top 1 million Tranquil domain names. This is because such domain names are more likely to belong to hosting services. Our results show that a lot of suspicious undelegated records, excluding that the correct and protected ones, are configured as test name servers. Specifically, we found that more than 1.5 million suspicious undelegated records at more than 6,000 name servers. Worse, we already found that a significant part of this kind of undedicated record were malicious. Suspiciously, the malicious undedicated records were detected at about 30% of tested domain names, and more than 18% of the tested name servers. Zoom into the top 5 vectors with the most undedicated record. We find that all of them are popular hosting providers, and notable proportions of malicious undedicated records were detected. For example, Cloudflare hosting over 3 million of undedicated records, and about 15% of which were proven malicious. Our result also shows that various different kinds of the malicious activities are related to this kind of malicious undedicated records. Most of them are C2 this kind of activities. We also conducted an in-depth analysis of 2 malware families that exploit Cloud DNS to obtain C2 servers, along with the cases of SPF record to hiding the SMTP-based convert communications. Yeah, you can find more details in our research paper. Here is the conclusion of this talks. We find an emerging threat model of convert communication that builds the reputation of popular domain names and the popular third-party DNS hosting services. So large-scale measurement study will confirm that the abuse of undedicated record is widespread in the real world. And last, please feel free to ask any questions and contact me through the email. Thanks.
Okay, thank you, Dr. Liu, for your very informative presentation. Any questions? We may have time for one question.
Maybe can I ask, so what is undedicated records? Because from my understanding, like the DNS provider like Cloudflare, they do require verification of ownership. For example, if I add a domain to the Cloudflare, they will ask for me to set the name server record. So that is a form of verification of ownership. And I understand that Google as well does this. So what I can understand that these providers do some sort of ownership, verification of ownership. So maybe can you give a brief description of what do you mean by undedicated records? Thank you.
Yeah, it's very important questions. Actually, you can find in the first part, you can find more details in our research papers, but I can give you direct examples to explain this kind of undedicated record. In the real world, a lot of popular DNS hosting services would like to attract more customers to use or to try this kind of DNS services. And in this kind of steps, the DNS hosting platforms would like to provide some basic functions to allow the customers to add some example resource record. This kind of functions are adopted in a lot of popular DNS hosting platforms. Yeah, this kind of resource record are not follow the strict policy of domain name ownership verification, and through a specific time, this kind of resource record will delete by the DNS hosting platforms, but it still provides an opportunity for the attack to abuse this kind of undedicated record. We believe this kind of undedicated records are not follow the domain ownership verification, but yeah, it is a result. It is a result of the DNS hosting platforms to attract more customers. Yeah.
Okay, thank you.
Okay, thank you. Now let's move on to the third speech. Okay, I'll introduce the third speaker first. This speech is made by Ms. Man Zhang. She is a DNS engineer at CNIC. Her research work focuses on the following areas: network infrastructure security, DNS threat detection, privacy enhancement, and protocol optimization. The second, analyzing applications and impacts of new security protection technologies in DNS, and optimizing network resource and system management mechanisms. Today, we are very honored to have Ms. Zhang to give us a speech named Delegation Issues in DNS. She will introduce the issues and security risks associated with DNS delegation. Let's welcome Ms. Zhang. Ms. Zhang, are you there?
I guess there may be some problem with Ms. Zhang to share the screen. Could you please
Okay.
change the order?
Okay.
Yeah.
So now I'll introduce another speaker. We'll wait for Ms. Zhang a few minutes. Okay. The first speaker is Chendi Ma. Chendi Ma is the engineer at the Industrial Internet and Internet of Things Institute of China Academy of Information and Communications Technology, primarily focusing on DNS security, in-depth data mining, and analysis. As a key technical professional, she has been involved in numerous national level and ministerial level construction projects. As a co-member, she has also participated in multiple projects under the National Key Research and Development Program of China with the theme of cyberspace security governance. Now, today we are very honored to have Ms. Ma to give us a speech named DNS Delegation Risk Resolutions in IETF Documents. She will introduce the threat mitigation plans in IETF documents, summarize all the plans, and give suggestions for the subsequent standard development work. Let's welcome Ms. Ma.
Okay, can you see my screen?
But we can also see your words. Okay. Oh, no, it's okay.
Okay. Okay, let's begin. Hello, everyone. I'm Chendi. Today, the subject I'm here to present to you is DNS delegation risk resolutions in IETF documents. In the DNS, the NS resource records instead of IP addresses separate a child zone from a parent zone. This makes it possible for domain name to depend on other domains in addition to its parent, which makes the DNS delegation relationships become more complex. Invalidate delegation, conflicting delegation, malicious delegation, cyclic delegation, and other bad delegation relationships are discovered, which induced many threats to DNS, such as domain hijacking, cache poisoning, not existence, NS attack, etc. As early as 1996, the problem of data inconsistency between different sources in DNS was concerned, and the credibility ranking was given by RFC 2181. With the increasing demand for DNS resolution, the risk in delegation relationships have been paid more and more attention. The DNS delegation threat response documents in IETF have an explosive growth this year. In this sharing, I'll first briefly introduce the solutions in each document, and then analyze and summarize the existing risk response plans. Finally, give suggestions for the subsequent standard development work. RFC 2181 gives the DNS data trustworthiness ranking, which considers that the DNS records of the child zone are more trustworthy than the referral response given by the parent zone. And based on this, the draft IETF DNS op NS revalidation proposed a scheme that is always go to the child zone to get the child's NS and go to the NS authority servers to query the IP of the NS. This data will be marked as more trusted in the cache. In addition, in order to prevent the ghost domain names, this draft also requires that all validation operations should be re-executed after the parent zone's delegation hierarchy have changed. Not exist NS attack shows us that the child zone may be a bad guy that will establish delegation records pointing to the victim zone. A new resource record named AOD is designed for DNS hosting service providers to record the relationships between NS and the hosted domain names. Recursive DNS send the query of the AOD resource records to the DNS hosting provider to find out whether the delegation relationships between the domain name and its NS are legitimate, thus effectively avoiding the resolution of malicious NS records. This can effectively deal with not-existent NS attack. RFC 7477 designs an automatic synchronization mechanism of the delegation records, which makes the parent zone aware of the changes of the delegation records in the child zone, and automatically obtain the update DNS data from the child zone. In this document, a new resource record Vsync is created, which can indicate the parent zone whether the delegation records need to be synchronized, how to synchronize the delegation records, and what resource records type should be synchronized. And it proposes a parental agent, which can actually modify the DNS delegation records within the parent zone for the child DNS operator. The way that the parental agent always actively synchronizes the delegation information for the child zones will cause great pressure on the parental agent, especially in the case of there's a large number of subdomains. Therefore, based on RFC 7477, a notify mechanism is introduced in draft IETF DNS op generalized notify to reduce the pressure on the parent when the delegation records in the child zone are changed. Especially, this draft creates a new resource record desync, which informs the domain name and the port of the parental data synchronization agent. When the delegated data of the child zone changed and need to be synchronized by the parent zone, the child zone will actively send update notify to the parental agent, and then the parental agent will copy and process certain resource record from the child zone, and finally sync the delegation records to the parent zone. In order to further reduce the data synchronization pressure of the parent, draft Juhani delegation DNS op delegation megamit via DDNS is proposed. This draft completely abolishes the way that the parent zone takes the initiative to query the child zone to obtain delegation information. The child zone takes the initiative to synchronize delegation records to the parent zone. And to verify the authenticity of the data, the child zone's public key is introduced. In the left picture, as the left picture shows, one way is that after the child zone actively synchronizes data to the parent, the parental agent obtains the public key to verify the credibility of the data. This method still needs DNSSEC to ensure the authenticity of the key. As the right picture shows, the other way is to build a data synchronization proxy on the registrar side. When the delegation data needs to be synchronized, the child zone sends its public key to the registrar agent through out-of-band methods, such as on the web, and then actively synchronizes data to the registrar agent. This mechanism doesn't need DNSSEC to ensure the authenticity of the child's public key. Okay, in the following, the solution in the IETF documents are summarized in the table. We can see that the solution plans are broadly divided into two categories based on their goals. One is to optimize the DNS policy on the recursive DNS to achieve more trusted delegation results. The other is to improve the consistency of the delegation data between the child zone and the parent zone in authority side. Each of these documents can address one or two types of bad delegation relationships. In the future work, we can also continue to explore optimization schemes for delegation dependencies from both authoritative name servers and the recursive servers. On the authority side, there is still a lack of systematic criterion to judge a well-zoned delegation relationship. In addition, to ensure that the parent zone is updated with delegation information from the child zone, protect registrant account safe, establish a delegation information update mechanism to avoid malicious updates, keep domain delegation records as simple and clear as possible to avoid circular delegation, single point delegation, and too long delegation, and check the validity of the delegation records periodically, etc. are also needed. And all of these demands need to be documented. On the recursive DNS side, the resolution plans of current documents can only deal with one or two kinds of bad delegation relationships. A more comprehensive solution is needed. In order to cover more delegation risks, it is often necessary to analyze the delegation-dependent relationships more strictly. That is, to adopt the principle of least trust to obtain delegation data from the more trusted authority servers as far as possible, and to combine with the data from the parent zone, the child zone, and the glue zone for comprehensive analysis. In general, this will make algorithm in recursive DNS very complex. So the implementation needs to be designed to be as lightweight as possible. Therefore, it is necessary to explore a more strict, lightweight, and comprehensive delegation confirmation protocol on the recursive DNS in the future. Okay, that's all. And I'm a poor English student, so if there are any questions, welcome to scan the QR code and add my WeChat for more communication. Thanks for listening.
Okay, thank you. Thank you very much for your informative speech. Anyone want to communicate with Chendi Ma? Or the third speaker, Ms. Man Zhang, are you ready for your speech?
Yeah. Okay, thank you, Asya. Okay, thanks for the introduction. DNS is a fundamental infrastructure for the internet. It implements hierarchical and distributed management through the delegation mechanism. DNS delegation includes multiple modes, each of which corresponds to different resource records, and there are also a variety of non-standard delegation operations. In addition, multipath delegation may also bring new problems while improving availability. The delegation information should always be kept in sync between the child zone and the parent zone. However, in practice, that's not always the case. Sometimes the parent and child assets may intersect, or one may be a subset of the other. In terms of TTL, the setting mechanisms of each node are also different. The value of some glue records are inconsistent with the A records obtained through active queries. It's required to set a certain redundancy for the authoritative resolution service, and at the same time, attention should be paid to rationality and effectiveness of the setting. For example, these name servers should be in different physical and location networks. In addition, the issue of concentration has become more prominent. In terms of data validity and availability for the delegation records itself, the counter referral response is not protected with DNS signatures, At the same time, the authoritative servers specified by the delegation records may have different connection or configuration errors during the deployment process. When formulating cache update strategies, although the APC has specified the data trustworthiness ranking method, many resolvers develop their own mechanisms, and some of which don't fully comply with the requirements of the APC. In addition, the above specifications of the APC don't include all application scenarios. Some hidden issues require active dynamic detection and a reasonable discovery mechanism needs to be designed. In addition to affecting performance and the load balance, the non-standard delegation can also create security risks, such as a third party gain control over the domain name resolution. There are still some unresolved issues, such as how to authenticate delegated records and as research when the above factors are combined, many attack possibilities can be generated. Researchers found that attackers can exploit vulnerabilities such as the lack of verification of delegation information, invalid records, and cache update strategy to design new attack methods. Some solutions have also been proposed for optimizing DNS delegation protocols. The previous speaker has provided a detailed introduction, so I'll briefly summarize them here. The first RC introduced a method to automatically keep records in the parent in sync through a periodical pulling of child using a new type record. Unfortunately, it lacked deployment. A second draft defines a new record which integrates the semantics of the DNS SVCB record and the name delegation function. The third draft proposed revalidation of delegation records. For example, when the resolver follows a referral response, it will do an explicit query for the authoritative NS asset. In addition to DNS delegation, the key management between parents and children in DNSSEC also requires a centralization mechanism. So researchers has conducted research on how to notify data changes and determine scanning frequencies. Our team led by Zhiwei is working with the Network Information Center of Chinese Academy and Science and Jinan University to carry out research projects related to DNS delegation security, mainly including security threat model design, risk pre-warning, and protocol optimization. Due to time constraints, we will not go into details here. Welcome to communicate with us via email. Thank you.
Okay, thank you, Ms. Zhang. Thank you for your worthwhile speech. Any questions for Ms. Zhang? If no, I guess it's all the speeches for today's session. And thank you all the speakers and also all the colleagues who have contributed to this webinar. And thank you all the participants. Your presence and active participation add immense value to the event, and it wouldn't be have been the same without you. Thank you very much. I guess it's the end of this webinar. Yeah.